Okay, I want to start video lecture 16 by talking about the issue of small sample sizes. That's covered in Statistics Without Tears on page 139 to 141. So this is this discussion of z-tests versus t-tests. So basically our normal distribution proportions that we've been using, the 68%, 95%, 99%, 99.7% that correspond to 1, 2, 2.5, and 3 standard deviations. Those, of course, only apply with good randomized samples over approximately 30. But when samples are less than 30, the standard deviation of the sample should not be used to approximate the standard deviation of the population because it's going to underestimate the actual population dispersion. And so if you don't correct for this with small samples, you can end up finding statistical significance more and more easily as the sample size decreases. And this increases the risk of making an error of discarding the null hypothesis too easily, right? So with samples fewer than 30, you're going to see a t-table being used, or what you're going to see is a t-score. Okay, so here's a similar diagram to the one on page 140 of Statistics Without Tears. And this illustrates, I think, pretty well the danger of small sample sizes, overestimating the significance of differences that you find between groups. So you see that the smaller the sample size, right, the proportion of extreme differences between two samples is going to increase. It's a little bit hard to see, but if you start here with your normal curve, that line comes here, right? But and then it shows here a sample of 5 that falls right here. And then with a sample of 2, look how this proportion that falls under the curve gets progressively more. So the smaller the sample size, the proportion of extreme differences between two samples is going to increase. So you use the t-table to solve that problem by, in fact, requiring bigger and bigger differences to attain statistical significance. So, for example, the book points out that to attain statistical significance at the 0.05 level, right, that would normally require differences greater than 2 standard errors of the difference, right, standard error of the difference. If you have a sample of only 4, the t-table would actually require a difference more than 3.2 standard errors. If you increase that sample from 4 to 12, then you only need 2.2 standard errors. And then as you keep approaching that magic number of 30, you get closer and closer to normal and just requiring that familiar 2 standard error of the difference. Okay, so just remember, with samples below 30, you're going to be using a t-table instead of what some people refer to as the z-table, the z-score, and that is sort of the familiar normal curve proportions we've been using. You're going to use a t-table, and just understand that with samples smaller than 30, you're going to have to show larger and larger differences between your samples to claim that statistical significance at whatever level you want. Okay, next I just want to mention the use of analysis of variance and the F-test. This is discussed on pages 141 to 150 in Statistics Without Tears. It's this idea of, well, what if you're a researcher and you want to compare results from more than 2 different samples? how do you do that? There are a couple of basic questions about this on the take-home test. So if you didn't understand it the first time you read it, you should probably go back and review that. But this slide, it illustrates once again the idea that the F-test can only be used with samples that are assumed to have similar dispersions, just like all the other mathematical tests we've been practicing with. Can't be used with samples that are going to have vastly different dispersions. So Roundtree, I think, explains this pretty well. He talks about the fact that if you were to take your whole group of samples and then just compare each set of two samples in your group of samples looking for a significant difference somewhere, you're going to increase the possibility of making an error of abandoning the null hypothesis. Because we have to remember that at the 0.05 level of statistical significance, right, we're assuming that 1 out of 20 comparisons is likely to appear to be significant simply by chance. Okay? And that's, that's with only two groups. But if you have more than two groups and you're comparing and contrasting different groups, each comparison you do has a 5% chance of looking statistically significant. So if you do a lot of those, you're going to increase your error, potential for error anyway. So for example, if you have 4 samples A, B, C, and D, and we set about to compare them all separately, comparing A and B, comparing A and C, A and D, and so on, what's going to happen is we're going to be more likely to claim a difference as real when it was really just due to chance because of the higher number of comparisons. Here's a sort of a larger picture of that graph that was on the prior slide. So you see here, if you're only comparing 2 sample means, we get right here 0.05 possibility of a type 1 error. That's if we're looking for the 0.05 level of statistical significance. And this diagram shows you how you increase your probability of error by doing too many pairwise comparisons of this many number of means. So the F-test gives you the ability to compare more than 2 samples at once and determine, basically it's sort of a binary determination. You can either determine whether all of the samples belong to the same population, in other words, there's no difference, or you can determine whether there's at least one group somewhere among your samples that seems to come from a different population. But be careful, right? The determination whether at least one group seems to come from a different population, that's the extent of the information that can ever be gleaned from the F-test, right? You can't tell whether all of your samples are statistically or significantly different, but you can answer the question whether one or more of your samples appears to be from a significantly different population. Are there one or more significant differences anywhere among these samples? Now, just so you know, there are ways to determine exactly which pairs of samples are different at a particular level of significance. And you can do this first and not even use analysis of variance to do it. This is just for your information. But if you're using analysis of variance, right, to figure out whether there's at least one group among your groups that appears to be statistically significantly different, you basically do the analysis of variance by comparing the variability of scores within groups to the variability of scores between your groups. And for this formula, you actually use variance itself and not standard deviation. So you're pooling the variability measures from within each of your samples to get an average within group variance. And then you average the variance between the sample means to get the between group variance. So you're looking at within group variance versus between group variance. And I think it makes logical sense if you just think about it, that if you're going to say there's a real difference somewhere among our sample groups, the between group variance should be higher than the variance within our groups, right? There should be a higher variance between groups if you want to say that there's a difference somewhere, a statistically significant difference. Okay, and if that's true, if your between group variance is larger, then you use an F ratio table looking at the variance differences to tell you whether that difference reaches whatever level of significance you're seeking, right? So you divide the between groups estimate by the within groups estimate, and then you go to your F ratio table to determine if you have at least one sample somewhere in there that's statistically significantly different at the level that you're looking for. So the amount of difference that you need to see, right, to attain significance in this context is going to vary depending upon two things. Not surprisingly, those things are the size of your samples and how many samples you're comparing. This makes I think perfect sense, even if you barely knew anything about this and you had to guess what would determine it. You'd certainly probably go to sample size and how many samples are being compared. And then lastly, you see on page 149 and 150 that analysis of variance can actually be used in some pretty complex ways. You can move from a one-way analysis of variance that's basically looking at only one basic attribute of samples, one measurement, but you can also look at more than one classification of samples, so more than one factor that you've measured. So for example, if you have samples of males and females and you want to see how well they perform on a certain exam, but you also think there might be differences in some other measurable attribute like stress level. So maybe here you devise a way to operationally define each subject as either stressed or not stressed, and then you'd also look at data with regard to those attributes. And if you do these more complex 2- or 3-way analyses, you're then able to examine all the separate components and combinations to see which experimental conditions seemed to create the most significant difference, right? Which of course allows you to then design your next set of experiments. So that's all I'm going to say about analysis of variance. And if any of this is unclear, just review that section in Statistics Without Tears. We are not mercifully going to have to do any calculations on these kinds of problems, but I do want you to at least try to get your brain a little bit up around the concepts, because if you're reviewing scientific studies in the future, you're certainly going to see this acronym ANOVA, and I want you to at least have a general idea of what might be going on when you see that. Okay, and then the last thing I want to be sure you also review is pages 150 to 154 in Statistics Without Tears, which covers the chi-square test. Those of you who have taken statistics might have worked with this. Roundtree doesn't include an example with actual calculations, so we're not going to do calculations for these either, but it's definitely something you're going to come across in the future, so you should at least understand the basics. So the chi-square test can be used when you want to compare differences between samples that have characteristics that are named by non-quantity variables. So these are category variables here. So we saw we can use standard error, the proportion, for comparisons between two category groups, right? like male and female, Obamacare supporters, not Obamacare supporters, and so on, right? We already did that earlier. But if you want to compare more than two attributes like this, then you need an alternative method. So more than two category attributes, you have to have an alternative method. And so this involves, as you saw in the book, stating a null hypothesis and then drawing up a table of expected frequencies of attributes or characteristics. Okay, and then you collect your data on your actual observed frequencies. And then you go to a chi-square table to determine whether the differences you observed are too big to be caused by chance alone. Okay, in other words, of course, whether the differences you observe are statistically significant, say at the 0.05 level or 0.01 level. All of those levels are represented in a chi-square table. So the example Roundtree has in the book involves equal samples of 100 males and 100 females and measures whether they have work experience or not, as compared to the 60% observed level of work experience in the entire sample of 200. Right? So Roundtree does the calculation and finds that the differences observed between males and females are significant at beyond the 0.01 level. So here, our overall level of all of the applicants that he looked at, 60% had work experience, 40% didn't have work experience, right? So if you assume that males and females in your overall population that's being looked at have the same amount of work experience, right? You'd put your expected values in at 60 and 60-40, right? Because that's your overall amount. But then what was actually found in this particular study is that actually males had a far higher percent that had work experience, right? There was 70% that did versus 30% that didn't, whereas females actually had a lower than expected level of work experience, right? And so the question was that difference significant? So this is the kind of chi-square table Roundtree would have used here, and the part that he leaves out of the book is that the table varies depending upon what is called the degree of freedom. That's represented here, up here, with this little DF on the table. Okay, so a simple definition of degree of freedom is that the degree of freedom is the number of values that are free to vary. Number of values that are free to vary. So for example, once you have one value designated, does that limit what the other value or values can be? All right, so I'm going to show you with our example. Okay, so here in our example, simple illustration of degree of freedom, you can see when you have a binary thing, right? It's a choice between yes or no, right? We know that once we know the percentage of males with work experience, the proportion that is no longer free to vary is over here, right? We know if we have 70% that do have work experience, that the answer of what percentage don't have work experience has to be 30, right? This proportion is no longer free to vary once we know this, right? Because there are only two choices. They have to add up to 100%, right? So if you only have two choices, right, you only have one value that's free to vary. This one can vary. Once this one is set, this one has to be the same, okay? So on the other hand, you can see if there were three categories here, say we had, instead of just yes for work experience, maybe we had two categories of work experience, one which would be major work experience, minor work experience, and no work experience. let's imagine that we had 3 categories, right? Then we could get a value for the first one, but the other 2 could still vary, right? And so in that sense, right, if you had 3 possible categories, you'd have 2 that are free to vary. So a study like that would be said to have 2 degrees of freedom. All right, but getting back to our actual example in the book, Roundtree was using this first line up here, right? Because there's only 1 degree of freedom when you only have 2 possible choices there, yes or no, for work experience, right? So there's only 1 degree of freedom, and he calculated, doing the math that is not included in the book, that the chi-square value for the data he used was 8.33, and I show this over here. Okay, and then he followed the table and saw that the 8.33 score here is beyond the 0.05 level of statistical significance. You actually would only need a 3.84 score to get 0.05. In fact, this score is in fact beyond the 0.005 level of statistical significance. Okay, and certainly beyond the 0.01 level of 6.63. Okay, and that is as far as I'm going to go with this. Again, review those last few pages. Make sure you at least have the very basic concept down, because I think I asked 1 or 2 questions on the take-home exam on this. Okay, that's the end of this lecture.